now we are going to start with a new characteristic of a chemical reaction, that is the half-life of a chemical reaction. Now, what do we mean by saying half-life period of chemical reaction? See, suppose in this beaker I have the reactants, right? See, so suppose I say when I start the reaction, the time is T and the concentration of the reactants are R. If we talk about the concentration. So, by saying half-life of a reaction, I mean that the time taken by the reactant, or you can say time taken by the concentration of reactant to reduce to half. Suppose as I told you, suppose the concentration of reactant is this much, right? And if I want to know that it gets reduced to this, right? Like it becomes half of the previous one. So, the time taken by the concentration of the reactant to reduce to half of its initial concentration is called as something half-life of a reaction, right? I think it's clear. So again I'll explain you with an example. Suppose we have a container, we have a few reactants in it, right? Suppose I say I have 10 moles of reactant in it. Then what is the time actually taken by that reactant to reduce its concentration from 10 moles to 5 moles. That means the time taken for the reactant to reduce its concentration to the half of its initial concentration. That is something called as half-life of a reaction, right? So, as we are concerned with the half-life of reaction, so that means we will have an expression for the half-life period for a reaction depending upon the order. Like for 0 order we will be having you can say an expression for the half-life and we will be having an expression for the first order as well. So, let us see that what is the expression or how we can calculate the half-life period of a chemical reaction for 0 order and for first order, right. So, suppose I have the 0 order reaction, we have any reaction of 0 order, and you know that for 0 order the rate is equal to, the rate constant is equal to R naught minus R upon T, we know that, right. And we also know that, like if we want to write the differential law expression, it is going to be rate of reaction depends upon rate constant, reactant raised to power 0 because rate is constant. And for 0 order we have already calculated that rate constant can be written as K is equal to R naught minus R upon T. This is what we have. So, this expression we are talking when the time is T and the concentration of reactant is R, right. Now, we just want to see that when we reduce the time to half period, that means the time becomes half of its when we start the reaction and the time is now half, we have reached in the mid of reaction, you can say. Then what happens, this R actually becomes half of the the initial concentration. This is what the half-life of a reaction means, that the concentration of reactant should be reduced to half of its initial concentration. So, this is what I have written. Suppose our initial concentration is R naught, right, and I said that when T will be half, then the concentration of the reactant is just going to be half of the initial one. Now, I am going to put this value here. So, what I will get after putting value, K is equal to R naught minus R naught upon 2 divided by time, and we are looking for this change when the time is reduced to half, right. So, I have just put T as T half, that means the half time which will be taken to reduce the concentration to half of its initial concentration. So, this is what I have. I will just simplify the equation. So, what do we get? See, it is R naught minus R naught upon 2, we take LCM. It becomes 2 R naught minus R naught, which comes out to be R naught by 2. So, I am just putting this value here. So, what do I get? I get R naught upon 2 time half. So, as we are looking for the expression for T half, so that means the expression for T half for 0 order reaction becomes this. So, this is something, the expression from which you can calculate the the half-life period for a reaction in which the reactant concentration is just going to be half of its initial concentration. Again, I think it's clear. Just look at the board again. We know this differential law equation for 0 order, right. We also know that we can write in this form also, that is K rate constant is equal to R naught minus R divided by T. Now, we are looking for the expression when the T will be half and even the concentration is going to be half. So, this is what I did. I reduced the time to half the period and I just reduced the concentration, that it becomes the new concentration should become half of the R naught, that is the initial concentration. I just put these values in this expression as R naught by 2. After simplifying it, we get this T half is equal to R upon 2K. So this is the expression by which you can calculate the half-life period of a chemical reaction of 0 order, only for 0 order. Now we look for the expression for the first order as well. We know that for first order, if we wish to write the differential law expression, we write in this form, that R is equal to K, concentration of reactant. You can take reactant as RA, any symbol you can use to denote it. So suppose the differential law equation, we know that it is this, that is the rate is directly proportional to the concentration of the reactant, right? And we write the expression in terms of K as shown. K is equal to 2.303 T log R naught upon R. This is what we have, right? Now we are looking for the expression when the time will be reduced to half and even the concentration is just going to be half of its initial concentration. This is what we took here. We are going to put the same value in this expression for 0 order. So it becomes K is equal to 2.303, time as T half, log R naught as R naught, and R is now expressed in the terms of R naught, that is R naught by 2, right? So I am just writing in the similar manner. So after solving, what do I get? I get 2.303 T half log of 2. And when I just simplify the result, you know what result I get? I get K is equal to 0.693 divided by T half, because we need the expression for T half, right? So this is T half is something equal to 0.693 divided by K. So this is the expression which we will be using for to calculate the half-life period for the chemical reaction for first order, right? So this is, I think it's clear that how you are going to calculate the half-life for the 0 order and half-life for the first order. Remember in in your mind that what is the expression which will be directly used in the the numericals. It will be for 0 order, it is going to be T half is equal to R upon 2K, and in this it is going to be T half is equal to 0.693 divided by K. So what conclusion do you get, that on what factors, like if we talk about 0 order, so on what factors this half-life, half time depends upon? So we know that, see that just look at the expression, by looking at the expression you can just tell that on what factors it depends. So T half we can say is directly proportional to the rate of reaction, right? Or we can say it is directly proportional to the concentration of the reactant, because the rate of reaction is something, the change in the concentration of chemical species with time. So we can say that for 0 order, T half is directly proportional to the concentration of the reactant. And we have one more factor, you can see that in the denominator we get K. So that means T half is inversely proportional to the rate constant. So for 0 order, if somebody is going to ask you that on what factors the half-life period depends, so you are just going to say by looking at the expression that T half is directly proportional to the rate of the reaction, or you can say the concentration of the reactant, and it is inversely proportional to the rate constant. That means if we increase the value of the concentration, T half is going to increase, and if we are just going to decrease the value of concentration, obviously the T half is going to decrease. Similarly, when we are just going to increase the value of the rate constant, T half is going to reduce, or you can say that they will have inverse effect on each other. And when we talk about first order, that on what factors this T half actually depends, so we see that T half, because we don't get any kind of R in the expression, right? So that means T half is independent of concentration of reactant. It do not depend, right? If you increase the concentration or you decrease the temperature, T half remains unaffected, but it is inversely proportional to the rate constant, right? So there is only one factor on which the half-life period for the first order reaction depend, and that factor is that it is inversely proportional to the rate constant. So this is the expression for 0 order or first order. I think it's clear that is what is half-life. Half-life is nothing, it is just that the time which is actually consumed to you can say reduce the concentration of reactant to its half of its initial concentration. So now we are in a position to solve some numericals based on this 0 order and first order. Just look at the board carefully.